Okay. Welcome everybody in this remote world that we're in. I'm Zishan Lakhani. I work at Fission doing applied research among some other stuff. I just joined a few weeks ago, but have been a big fan of everything they've been doing so far in terms of all this kind of outreach and community as well with the distributed systems reading group. I said Brooklyn and Philip run. We also have the different kind of Fission working group meets, including for research on Reactor, but we also have stuff, around UCAN and all this other stuff. I highly push or promote people to go look at the Luma page and the Fission website for more information there. As for me, where this kind of thing came to be is we have a distributed systems reading group already. That's awesome. We kind of lay those out per month in the year, but of course, like most people, there are papers that just come that you hit that you want to read right away because they might be very apparent for the work that you're doing. In the meantime, Quinn, who's on our Fission team doing a lot of research in the applied stuff there, gave a great little cliff notes on this paper. But we come across a lot of papers. We're always talking about papers, and this one was one that Blaine, who just joined the team as well, was like he brought it up in one channel. I think Brooke brought it up in another channel. I brought it up in another channel, and we were like, "Hey, we should read this. Do we need to get an internal group going?" I was like, "Well, why don't we make it public? That's the Fission thing to do. We have a great community," and I was like, "Cool." And then I think something happened where it's like, oh, what if the authors want to come and join and give an intro and be around for answering questions? And oh yeah, that's a great idea. And Shadaj and May, I messaged them, I think hours later, they were like, yeah, we're in. And I think this fits in good with the release of the code and implementation stuff. And I know, yeah, I've been watching the GitHub repo there. So without further ado, this is how all these things, and we're going to be doing, I think, a few more of these things where bringing in the authors or people related to the content, and we'll get together. So hence papers with friends, as we have a lot of friends here. Everybody's friends here. So now to this paper, and I wrote some questions, but I think people probably have questions here, and since we have authors on, that's always really awesome. This is Katara, Synthesizing CRDTs with Verified Lifting. This is a really cool paper mixing, I would say, concepts that we know in systems of CRDTs with programming languages and program synthesis. So before we kind of get into a discussion phase and questions and stuff like that, Shadaj, do you want to give us kind of an intro to your team's paper here?
Yeah, sure. So hi, everyone. I'm Shadaj. I'm a second-year PhD student at UC Berkeley. I work at the intersection of distributed systems and programming languages. So I'm co-advised by Joe Hellerstein and Alvin Chung. So I kind of have one foot on either side. So yeah, this paper actually ended up coming out kind of a bit surprisingly. So when I was a first year, I was just discussing with Joe about hey, what are interesting things? I have this background in programming languages. What are fun things we can do? Joe is pretty excited about using verified lifting, which is the kind of research that Alvin developed to use program synthesis to translate programs from one domain to another. So we actually started with actors as the original thing that we were focusing on. So you're looking at, so a lot of my background actually is I've been involved with the Scala open source community for a while. So I knew a lot about actors. I'd done a bunch of stuff in Akka. So I was like, hey, maybe we can do some synthesis where we take existing actor programs and lift them into this new declarative distributed systems language we're building. So I guess the wider context is this project is part of the larger Hydro umbrella at Berkeley. So if you read the Pact for Cloud Programming paper, this lays out this larger Hydro vision where we want to build programming languages and compilers and optimizers built around a declarative data flow, taking advantages of things like monotonicity analyses and things like that. So the original idea was, can we take actor programs and lift them into this monotonic declarative language? And then over time, kind of as we started reducing and kind of more constraining the problem. We were like, oh, the communication between actors is kind of hard to model and analyze. So let's focus on just local state transformations. And eventually we realized, hey, we're dealing with normal sequential data types at this point, if we're not focusing on the communication between nodes. And if we're lifting into something that's monotone, that really looks like a CRDT. So that's how we kind of ended up landing on this problem. I guess what would you like me to intro about this paper, Zishan? I can give the whole summary, but
yeah, I think maybe because I think specifics and questions we'll get to some of the technique stuff. I think maybe like kind of maybe a good overview of the motivation. I mean, you gave a little bit of that, but I think really that would be probably a really good thing about kind of the motivation piece of the section to kind of get everybody even keeled with like what we know about and stuff, and then we can get into more of the kind of specifics on the synthesis techniques and the algorithm and stuff like that. People have it for discussion points.
Yeah, sure. So I guess the key motivation is CRDTs are really cool and super powerful, but they have kind of a bunch of layer of requirements. So first, there's kind of the core properties. So focusing on state-based CRDTs, which are what we focus on in this paper, your state has to monotonically grow. You have to have this associative, commutative, and idempotent merge function so that you can support arbitrary gossip and not depend on the orders or when the protocol decides to issue gossip. And then you have this convergence property, which is this kind of a little bit loose property, especially on state-based CRDTs. But the key idea is that regardless of the order in which you receive different operations on different nodes concurrently and they choose to gossip to each other, everyone eventually reaches the same state. So actually guaranteeing all of these properties while preserving the application semantics that you're specifically targeting, because CRDTs often have to be tied specifically to different application use cases, is quite challenging for developers. And so that's kind of what led us to this is, can we provide a way for developers to specify their custom application semantics? So that's the sequential data type. Can we allow developers to reason about tweaks they might have to make in order to transform that into a CRDT? Because normal data types don't necessarily have an exactly identical CRDT, but something that's pretty close. And that's what we see with classic CRDTs, like different variations of set CRDTs. So how can we make that succinct, the tweaks that are going into the semantics between the original and the CRDT version? That's the operation ordering. And then how do we make this whole process fully automated? And that focuses on the verification side. I think there's already some excitement around doing automated verification of CRDTs. So there's this paper at CAV 19 on automatic verification of convergence in CRDTs. And so kind of we thought this was the right time to kind of take that a step further and focus on verifying CRDTs with respect to an existing data type instead of just verifying it locally, and really bringing those application semantics into how we reason about CRDT design. Yeah, May is here also, so she can talk more about this.
Yeah, sorry, everyone.
Do you want to add anything?
Yeah, I had massive computer trouble this morning, so I'm sorry for being late for this. Good to see you all. I'm really excited that you guys are really excited about the work. I'll add just one more piece of context, which is this work comes out of basically 2 lines of research. There's part of the Hydra project and is a major part of like satisfying that packed framework, which I think Shadaj already gave you the link to the vision paper that Joe, Alvin, Natasha, and I put out a couple years ago. But it also has motivations from the Gallifrey line of work, which basically said, what if you had sequential data types and you could have a way to lift them into CRDTs, and then you build a programming model around concurrent access to these sequentially specified data types? That line of work actually just kind of hand-waved how such a lifting could occur. So this is the first result that says, by the way, there is actually a way to do that translation, and here it is. And so I'll just dump a link into the chat for that. So the motivation for like, why would we do this to CRDTs was partially like, it's just well motivated independently. And it was partially like, I wrote a thesis and I left a chapter out. Let's finish it.
That's always a great reason, actually, to do that. But yeah, before we kind of open it up, one thing that I'll kind of bring in kind of and some of the high level stuff when I highlighted this was like, having worked at Basho when we worked on putting CRDTs into React. I know Russell Brown is here somewhere. old friend of mine, and coworker from those bachelor days, who still works in CRDTs today. But one thing that kind of comes into this is, the hard problem. You talk about, I think, the key premise I highlighted, like constructing correct CRDTs is difficult, posing a challenge. And I think this line of working with CRDTs, having programmers try to write or understand the operation of CRDTs has been, a long, as long as CRDTs have become kind of, somewhat mainstream or somewhat tangential to mainstream, this has been this issue, right? So maybe you could talk about just a little bit how you kind of view that motivation, because as much of this paper is a convergence of systems and programming languages, and I'm trying to be the pun on convergence there. It's also there's a little bit of this HCI kind of factor as well, right? Of how people can work with these things and thinking about sequential programs this way. Can you talk a little bit about how that's how all this is driven from the user perspective? Because it also falls in line with the synthesis techniques and stuff like that as well.
Yeah, so I think that's one of the key parts of verified lifting, especially kind of as a specific sub area of program synthesis work, is it's fundamentally been focused on, at the end of the day, we want to provide the abstraction of effectively a compiler to the developer, right? Rather than being super involved throughout the process, you want this to be something where I just throw my existing program and it spins and maybe spits out a lot of heat and it produces the thing I want in the target domain. So we were fundamentally driven by that. And a lot of past work has actually been fully automated in this way, where they're able to, and actually this is one of the first pieces of verified lifting work that does a little bit of semantic tweaking with annotations. But classically it's been, I want to produce a program that actually produces the exact same output, but uses a different computation technique. So for example, taking sequential imperative Java code with a bunch of for loops and converting it into an exactly identical Spark program. So we were fundamentally driven by this goal of, hey, it's really hard if we're going back and forth with the developer to quickly search this very large space of CRDTs. So any additional information we do take from the developer has to be provided ahead of time. And that produces a bunch of interesting restrictions. For example, if the user is providing this operation ordering annotation, it can't be in terms of theoretical CRDT, because the developer doesn't know of any CRDTs that we're going to be testing out yet. So the operation ordering has to be in terms of the sequential data type, which ends up working really nicely because it's easier for a developer to think in terms of the sequential data type than the CRDT that may exist down the line. So I think that kind of really, it constrained and also ended up producing this nice design where the developer writes this existing C++ code base. We're actually currently working on adding some more automation that helps guide developers through the creation of the operation ordering, because we're able to check some things ahead of time to make sure that things make sense. Because if we can detect operations that are not commutative, we can tell developers, hey, you need to provide me an ordering for those operations. So we're actually working on some automation around that now. But the idea is this is all something that happens ahead of time, so that when this much more expensive, relatively synthesis procedure is happening, the developer can just kind of sit back and sip their coffee.
Yeah, I will also say that independent of the specification of CRDTs, their use provides lots of programmability questions that have never been adequately answered by existing work. The paper we're about to talk about today isn't really focused on the case of using CRDTs so much as the case of building them. But our group at large is very focused on the question of brilliant, you have a CRDT, what do you do with it? And we just submitted revisions on a VLDB paper that sort of outlines our vision for how are CRDTs to be used? What is the right? I mean, CRDTs are great as long as you don't look at them. How can you look at them and actually have something useful come out? And there's also a programming model around them in Gallifrey, which is relatively constricted because it has to be a coherent language design. And if you read our VLDB paper, which will, show up on the archive soon and be at VLDB sooner, maybe, we're not very good at archive, you'll immediately not be surprised if you've read any of Joe's work for the last 15 years or any of my work for the last 10, that the answer is monotonicity. And I know I've seen your website, that that's something near and dear to this community's hearts. In terms of programmability studies, though, in terms of have we actually sat a user down and seen how easy it is for them to use these specifications? The short answer to that is only experts. We've had several undergrads come by. We've done not necessarily rigorous studies, but an attempt, or at least during the language design portion of this, we put a bunch of people in a room and said here's the basic idea of syntax. Here's your task. Whiteboard out how you design this program, and use that to influence the design. But now that the design exists, we haven't done the work yet to go back and sit down and recruit a new set of participants and say all right, here's the actual honest to goodness tool, go. And I think in general, formal programming languages as a community has a problem with user studies. There's the widespread, perhaps even universal tendency to publish your paper. Do use user studies for the formative portion if you need, but as soon as you publish your paper at PLDI, that's kind of it. There isn't the necessary follow-on work of, all right, a year later, once we've gotten the error messages good, can anyone use it? There's a couple of exceptions here. At Berkeley, Sarah Chasen's entire group is very committed to answering those questions rigorously about everything they do. And that gives us the opportunity to collaborate with a team that is very actively invested in the question of, can users use your thing? So we look forward to exploring those opportunities.
Yeah, I want to say that's awesome. We can maybe push that even to a later thread, because I think that's a whole thing, right? I mean, there was Michael Kovlin's work at UPSLA a couple of years ago on blockchain programming stuff, but they try to do this kind of mixed user study. So it's a really interesting thing. So it's actually really great you brought it up. And you're right, most things in PL, having done a lot of PL research, right, we don't think about that too much. So I think that's actually a great thread to this, which is and very cool on the VLDB stuff. So maybe what we'll do, since we have May and Shadaj here, we'll open it up to some discussion point questions that people want to ask or kind of go further into. So if people want to raise their hand. I guess Quinn has her hand raised, what I see. So Quinn, do you want to go first?
Yeah, sure. Hi, May. Hi, Shadaj. First off, I absolutely loved this paper, and I've also devoured kind of everything around the whole Hydro project, and just the work you're doing is really amazing. Something that stands out to me in this paper is that this feels like it's just kind of the start of what you want to do with this verified lifting framework. And especially in the PAPT paper, you talk a lot about wanting to synthesize full programs down to this hydrologic IR. That's a data log based language, determining which parts of the program are not monotonic so that you can separate those out effectively. And I guess I was curious about what the next steps are in terms of applying this verified lifting framework to that synthesis problem, and whether you found success with these techniques in any of the other areas that you're targeting. I realize that's kind of a long-winded question, but just that's all such an ambitious goal, and I'm really curious about where else you've applied these tools and where they're working.
Yeah, you're very right that it's ambitious. Yeah, maybe I can speak as kind of what is the immediate follow-up work that we're kind of excited about. So you mentioned data log, and kind of we are trying to build out this kind of IR that is inspired by data log as the data flow programming language that kind of be exposed at a higher level. One of the first steps that we're kind of excited to shift this work towards that direction is synthesizing CRDTs that support more complex iterative logic under the hood by using data log as a target language. So right now we have this functional-ish target IR that supports reductions and some very simple forms of iteration. But if you want to synthesize something like a text-based CRDT, then your challenge becomes much more complicated. And there's some really exciting work by Martin Klutman recently on modeling everything in terms of data log that we're pretty excited about.
Is that the RGA work?
Sorry, what?
Is that the RGA work you're talking about?
Yeah,
okay.
Exactly. Yeah. So that's I think that's going to be the first direction that we start pushing towards that kind of more general purpose program synthesis. I will say it's quite challenging. Program synthesis, when it works, is really fantastic. But if you look through a lot of the verified lifting papers, almost all of them, one of the key kind of pieces of the puzzle that you have to figure out is what's a quick way to rapidly constrain the search space. In our case, it was we identified that the state of a CRDT should be a composition of semi-lattices. And that has a drastic effect on simplifying the search space that we have to explore. It is yet to be seen what is that cool trick that we can apply for data log, because it's a much wider and much more open space. But I think kind of as a general Hydra group, we've been kind of curious about using synthesis in more areas. So one of the things that has been is, if we want to achieve this dream of taking existing backend applications written in frameworks like Spring and things and bringing them into this world, is there synthesis we can do at like the application database edge, and kind of reasoning about exactly what the application requires from the database? Can we infer opportunities to use replicated data types where currently just a traditional SQL database is being used? But these are a bit out there, I think. Synthesis has definitely improved significantly in terms of just like raw performance, but I think there's some kind of key jumps that we have to make before you can start doing these like very large programs through synthesis. But we've been actually working, so there's another student in Alvin's group, Sahil Bhatia, and we've been working together on building out this more general purpose framework for verified lifting, and we're trying to bake in a lot of these optimizations into there so that it can enable future work that's more large scale.
Awesome, thank you. That's MetaLift, I'm guessing, and
MetaLift,
I saw
yeah.
there's the other paper on using verified lifting for stencil computation. Are there
there's a
areas
bunch
where
of
it's
past
being
work.
applied to
MetaLift is trying to kind of
success?
bridge all of those. So all of the previous papers in verified lifting. So Katara is actually the first one that's actually built on top of MetaLift. A lot of the previous papers were kind of using their own kind of hand-thrown together verified lifting systems. We're trying to unify those.
Okay, cool, thank you.
There's also past work in Java to SQL, C++ to various graphics things, I think Halide.
Yeah.
And I will say that more generally, the way the Hydra project is proceeding right now is pick your favorite part of this giant pie in the sky vision and do it. So it's less like start at synthesis and explore outward, and more like we have a bunch of students, they're all working in exciting places. 5-year visions are in research, not so much what you want to do within 5 years as the direction you want to be walking for the next 5 years. The mountain might still look just as big and just as distant after 5 years, but it's still there, which is lovely. Yeah, and concretely, Shadaj is right that the key to making synthesis work is to limit the search space. So in parallel to all the work Shadaj outlined, we've got a student who's working on basically a characterization of what existing cloud programs do, in the hopes that we can find some cloud programs that sort of fit the Gallifrey model of secretly just make them sequential programs that communicate with CRDTs, and cloud programs that fit more like the traditional data flow model of secretly just make this a streaming computation. If we can get some confidence that a large number of micro-benchmark or cloud-based applications are already built this way because of existing infrastructure, then what we have is a bunch of small synthesis targets, not one big, just to send everything into data log and be done target.
Cool. Yeah, I was gonna say,
Really helpful,
synthesis as a hammer is really interesting. Is a really big piece of this, right? How big of a hammer can it be, right? Sorry, Quinn, go for it. You're saying.
Oh, I was just saying thanks.
Yeah. Cool, Jesse. I think you have a question.
Thanks. I'm going to do a quick screen share just to look at the chunk of the paper that I wanted to ask about. Just a detailed question about this equivalence function, that a query on the sequential type should produce the same answer as a query on the equivalent CRDT. And I'm wondering why there also has to be a relation function that directly compares the two, since it seems like having the same answer from the two queries should be enough. And I really liked the elegance of this part, saying that if the two things have the same observable behavior, then they are equivalent. And so this part sort of made me feel bad because there seems to be something that I'm missing. So I'm curious what purpose that has.
Yeah, so this is actually the fact that we check that queries are identical is something we added like maybe 2 weeks before our paper deadline, and it's the only thing that made the paper work, which is kind of crazy.
Yeah, that was very exciting.
So maybe we can take a step where we don't have to query. The key idea is this equivalent kind of way to relate to the CRDT and sequential data type state is acting as an inductive invariant, and it's making this inductive proof go through. And what you have to do is kind of, I'm trying to think of what's a simple example where you do need the relation. Does it work for two-phase sets? Maybe I'll think in the back of my head of trying to come up with a good concrete example. But the key idea is when you're comparing two states, you have them in one point in time. But the role of the equivalent function is not only to guarantee that they are behavior equivalent at that point in time, but that after any sequence of operations, they will remain equivalent. And so oftentimes the equivalent needs to be stronger in order to provide those guarantees about what will happen after operations. Because you could say, especially if your query is very limited. So for example, you could imagine a much more lightweight version of the query where you say, does, I don't know, the element 5 exist or does the element 2 exist or something like that. And if you have that query that gives a very partial view into what is the full state of the CRDTs, and so the idea is the relation reasons about all the things that the query can't see that are necessary to prove that the query will remain identical later on. At the end of the day, the queries are what matters, but I guess this relation is reasoning about future queries after operations execute and providing the necessary guarantees.
Yeah, thanks. That's helpful.
Cool. One question that I think someone had on the chat, and maybe you all can talk about this more at the higher CRDT level, was what are the convergence issues that people have with CRDTs, or what are the convergence issues that do occur? I think this gets into a little bit of a larger question about CRDTs in general, but maybe, I don't know if you all have some thoughts generally about that. Yeah.
So there are two questions kind of hiding here. One is like, how do the CRDTs themselves converge and how do we ensure that? I'll toss that one to Shadaj. The short answer is semi-lattices are cool. And the other question is, it goes back to programmability. What are the threats to overall program convergence from using CRDTs? We'll answer that one second. So let's start with how do CRDTs themselves converge?
Yeah. So I guess so. I'll go into kind of what our system does to guarantee convergence, and then maybe we can have a broader discussion of what convergence means in general. So the key trick that we use for convergence is the fact that we already have this merge function, which is associative, commutative, and idempotent. And that already is kind of doing part of the work towards guaranteeing convergence by making sure that gossip is safe. When nodes are exchanging their state with each other, regardless of when they're merging their states, eventually that gossip will get everyone to a common state. The other piece of that puzzle is the actual execution of operations, because if operations are doing arbitrary logic, you can end up in situations where, depending on which nodes gossip in which orders before or after an operation executes, or the order in which operations are propagated across different nodes, you can end up with divergence. Our trick is to say, we already have this merge function. It already gives us the guarantees we want. Why don't we just use this within the operations themselves? So the way we actually structure the operations in the CRDTs we synthesize is that every operation just merges the current state with this delta. And the delta is computed as a function of the operation parameters. And so this guarantees us commutativity of operations because this delta only depends on the set of parameters. It doesn't depend on the state. There are edge cases. We have this non-idempotent CRDT synthesis where we do leak a little bit of the state into it, but the general principle is that because we make this delta independent of the current state of the CRDT and have the only thing that reasons about both the current state and the update be the merge function, which already has the ACI properties because it is derived from the semi-lattice, then we can guarantee safety without actually having to bake that into the formal proof. I will say there are actually techniques. So there's this CAB19 automated parametric verification of CRDTs. Really, really great paper. Actually, that kind of is what inspired our approach to constructing this SMT proof. We ended up doing very different things. We're checking very different properties since we guarantee convergence by construction, and they're worried about proving convergence. But it's very fun to see kind of how related papers in the space kind of end up using similar tricks to perform verification.
Cool. Yeah, I was going to say one thing on that, which is maybe we can. I know there's part two that May was going to mention, but I guess the interesting thing here is these sides of where correct by construction CRDTs and synthesizing them versus the verification side, which is you expect people to write you get people to write CRDTs and you want to verify essentially that they're doing the right thing, right? And it's interesting that there's the attack vectors of these things come from both sides, but it's cool. I was going to ask actually later how you kind of shared techniques there with that paper, but that's a good point that you made anyway. May, please, if you want to get to the part two we're talking about.
Sure. There's a question in the chat, which is how do you use this delta approach with an op-based CRDT? Very simple. You construct an empty instance of your CRDT, then you apply your op to that, then that instance is now your delta. So you can just gossip that instance. It's pretty much how it's specified, actually. You can always turn an op-based CRDT into a state-based one by taking this approach. In terms of overall program convergence, the main threat is observing temporary impossible states. Let's say, for example, that you view your CRDT computation as something that should be linearizable, something that should appear as though there's a single replica out there that everyone's communicating with. And Zishan and Quinn are both adding an item to a set. And I'm sitting here and I've got an instruction that says, if the set has, or even better, Quinn sends an item number 5, and then like 2 days later, Zishan sends an item number 7. And if I'm sitting here with running code that says if the set contains 7 but never 5, then I should launch missiles, or then I should withdraw my entire savings account, or then I should move to a new state. Some very obvious, very public action that would cost me to retract if I can retract it at all. There's probably not going to be a final linearization of the system that somehow makes an operation that occurs 2 days later appear to occur before an operation that initially happened. But with CRDTs, there's no guarantee on order. If I happen to be working very close to where Zishan's replica is, or off of Zishan's replica itself, there's a quite large chance that I will temporarily see a state that's impossible in the final linearization, and I will have conditioned a control flow decision on the observation of that state. This is exactly the case we're talking about when we say that there is a possibility of a convergence issue in the program. Basically, it manifests as a consistency issue if you think about it as reasons and rights, because they are two different ways of talking about the same thing. And in summary, it means that if my program was running at Zishan's replica and at Quinn's replica, it would make different control decisions at Quinn's versus Zishan's that would be unreconcilable in the overall program. Okay, Quinn, you got a question?
Yeah, it's a few minutes ago, Shiraj mentioned that there's a couple convergence questions for the non-idempotent CRDTs. And I know in your case, you're handling non-idempotency by introducing like vector clocks that map the node ID to the updates for that node. Do you have any other approaches that you're applying for cases where there's an unbounded or unknown number of network or nodes on the network, or where like the topology is changing dynamically?
Yeah, that's a good question. So right now, no. So the handling of non-idempotent is very heavily kind of directly inspired by how classic CRDTs handle this. So if you've seen PN counters, they just say, assume that every node has a unique ID and magic happens. And we kind of just lean on that for now.
Okay.
I think the trick would be if there are kind of strategies for generating equivalent kind of identifiers or something that can be more tolerant of changing membership, then you would just map those in. But from our perspective, what we care about is ensuring a single writer for chunks of state. So that is what allows us to safely handle non-idempotent operators.
Yeah. I will say, sorry, it's worth noting that you do have a unique ID for every node. IPv6 is built so that you have a unique identifier for every node. You have a good sense as to how many bits you need for that. And that will work. So you just kind of treat everything as a map from an IPv6 address to whatever you're storing. No more conflicts, single writers all around.
Okay. Sorry, I had another point off of that. Oh, yes, kind of reading between the lines. In the PACT paper, it mentioned that you also want to do like content-based networking and content-based addressing and so on. And I thought that that might have been connected to this non-idempotent point because Martin Kleppman writes about building like Byzantine fault-tolerant CRDTs using like a content addressable DAG that does explicit causality tracking. And I guess I was curious about whether that fits into your approach at all, and if that's something that you've been thinking about. The idea being that you like directly link the facts together based on their provenance, and use like the cryptographically secure hash functions as essentially like unforgeable like history pointers.
Yeah. I will say that we don't need that power.
Okay.
If you want to have a secure CRDT setting, then you'll need everyone to sign everything as always. If you're looking to do a TARDIS style causality tracker, you'll need to basically turn your entire causal history into a hash chain, which is roughly, I think, what you were just suggesting. All of these things are possible, and they give the extra power the PACT paper claims that they will. But none of them are particularly necessary or particularly useful in the convergence and multi-writer sense for CRDTs. Since as far as our CRDT design works, we don't really have the ability to do a TARDIS style, everybody just lists their previous message, because we assume this very open CRDT world where it's not possible to wait for every replica to get every update. And in a chaining update, you actually just break down if you're missing like the middle third. You no longer have any idea how things before that missing chunk are related to things after, and that's important to us. So we need to have a CRDT representation that doesn't rely on having all of history. For that one, just having a way to generate unique IDs is enough. We know if we got 64 bits, we're good. So from there, how you generate that is really depends on your specific security assumptions.
Okay, cool. Thank you. So I honestly don't know too much about IPv6. Are you currently targeting like non-Byzantine environments?
I think that's the
Is that
initial
like
target.
IPv6?
Yeah.
Okay.
It's worth asking, if I have a CRDT and it's shared among some Byzantine and non-Byzantine actors, what can the non-Byzantine actors do? So if you've solved the convergence problem by via signatures or via using the routing layer to introduce those identifying stamps rather than the individual actors, and you have a non-Byzantine routing layer, then you don't have to worry about any convergence threat. And most CRDTs don't have convergence threat in the first place. So at this point, you've got a Byzantine actor that has the ability to arbitrarily manipulate a CRDT. That's would be its behavior following protocol, because we don't assume anything about the programs in the first place. There's not much behavior left the Byzantine actor has access to really manifest its Byzantineness. Any amount of screwing with the actual API of the object is allowed. Okay.
So there's no risk in this case of someone sending events using Sonos's like IPv6 identifier and breaking
if you have trusted routing infrastructure, then no, that just won't route.
Okay, awesome. Thank you.
But if you don't have trusted routing infrastructure, just sign it.
Okay.
Yeah, and even with trusting routing infrastructure, it has like HMAC signing at every point and stuff like that, right? If you start looking for that direction. Right?
Yeah, I guess I meant trusted routing infrastructure as in somehow you know the routing infrastructure will only route the valid requests, as opposed to it's in my specific basement and I personally know the engineers.
Yeah, or like a really bad ISP or something that's really mean and deceitful. The ultimate Byzantine. Maybe to that, because I see Mark Antoine's question. I agree that we don't want a full history, but would the same reasoning apply to events pointing to a partial locally known history?
So there's a lot of work in like a local prefix consistency idea where you kind of view the world as having there being some global history and some local history and some missing stuff in the middle. That model was popularized by Microsoft a couple of years ago. Actually, a funny story, because they needed something for their like online Scratch programming environment. So they came up with this whole cloud types framework because they asked Mark Shapiro and Sebastian Burkhardt to weigh in, and they got more than they bargained for. So fun history aside, It depends entirely on the semantics of your object and on the consistency tolerances of your user. If you're going for CRDTs, then you're going for this full convergence property. So that missing third has the opportunity to be causally related or causally unrelated in any way. It can, in fact, force a linearization before the original segment. In order to have this view of the world where there's something that has happened and we know about it, something that hasn't happened and we're waiting for it, and then us, you need to have a strong notion that the middle chunk, the something that's happened that we don't know about, actually linearizes in the middle. And you only really get that if you've got some sequential service or some highly fault-tolerant service that's officially blessing prefixes, so that you can be guaranteed you actually have a prefix and not just random snatches of things that'll go in random orders in the middle. If you don't want to have such a service, then you need to do the CRDT approach of making sure that your events are orderable independently of a sort of chain of history. At which point you can construct the chain of history locally and you can reason that, well, there's a vector clock gap here, so something's probably missing. Or those messages are lost to time forever, and I don't know. Our CRDTs have to be robust to that. Sorry, I should let Shadaj take a swing at this too.
No, I think you covered basically kind of the key points in that a lot of the things that happen with what types of queries you want to safely execute ends up being much more of a question of the application's consistency constraints, which CRDTs kind of don't really, like the design of your CRDT is typically not affected by your application consistency constraints. It just has this uniform guarantee of convergence, and that's all it'll give you. There are things to reason about in terms of like application semantics of how does the CRDT deal with concurrent operations and stuff like that. But I think that's a little bit, they're very related and you're in kind of a bit of the same mindset when thinking about it, but it's a bit different than thinking about the consistency that you get when pulling data out of the CRDT.
Yeah, for sure. And we're not sitting here saying never read your CRDTs. That's kind of defeating the point. If I was saying never read your CRDTs, why bother gossiping them? We have, again, I'll just make a plug for the upcoming VLDB paper that basically outlines a query model that shows you what you can always observe from CRDTs using only local history, or only local history plus whatever you happen to have heard of, while still preserving overall consistency and convergence of your application. Which is useful. Gallifrey also has a long diatribe about how to make it safe to observe CRDTs. So if you're looking for just like, okay, well, how do I actually use these things responsibly? Great question. Go research that. But also we have a couple of results.
Cool. So one question I was bringing up, kind of going back to this non-item operation stuff and the node IDs. There's a part in the paper that talks about future work, which I thought was really interesting from a program analysis perspective, which is how to automatically detect non-item potence. I wonder, that's probably again part of, it's future work question, but seeing what you are thinking in that space, because to me that's a pretty hard problem. So from the again also the usability perspective. So
yeah, it's something that's kind of being cooked right now as we speak. I'm working with an undergrad at Berkeley, and basically the key trick is we are boiling down checking for idempotence into SMT. So we take your existing program, we encode it in SMT, and then it's relatively simple. So for example, right now our definition of idempotence is on the sequential data type, run the same operation twice, you get the exact same state. That's not quite as precise as you would like it to be, because you might have changes in the state that don't actually affect downstream queries. So we're planning, maybe we can do some synthesis to do a little bit of pruning to say that, oh, if the system claims that this state was different, can we actually show that that results in downstream query divergence, or does it have no effect? But at least initially, in most cases, we're actually just able to do this simple check. But it's more like a developer help initially, and then eventually it'll just be an automatic flag. One of the nice things is enabling non-idempotence in our system just adds more stuff to the grammar. So it makes the synthesis procedure a bit slower, but it's okay if you turn it on by mistake. So it can be we can have a little bit of a conservative analysis. And it's okay if it turns on every once in a while. Your synthesis procedure will be a little bit slower, but it automates a bit more of the things end to end if we can do that detection ahead of time. But yeah, that will be maybe. I'm optimistic that we'll have it like out open source maybe in like December or something. But yeah.
Cool, very awesome. Scott Fritchie.
Hey, hi there. I have a question that's actually from Sam Elliott, who isn't here, but it was in an XBasho chat, and Russell and I have been talking in the background, and hopefully it's okay to borrow Sam's question there and ask y'all. This was back on October 8th, and he had just read through your paper and really liked it. And one of the things that he said back then was, I'm interested that they found that they didn't need version vectors, really, that I wonder what happens if you offer them as a primitive and tell it to avoid stuff that you cannot prune. I was wondering if you had any reaction to that. I didn't actually read the paper. My apologies, I was off by a week in scheduling my reading. So I've just been lurking, but this is again through Sam Elliott.
So I'm assuming when you mean version vectors, we're talking vector clocks, right? Yeah, okay. So that's a really good question. So we actually originally were targeting just using vector clocks in these situations where you need to reason about what operations are commutative and not. We ended up settling on Lamport timestamps, which are kind of a lossy. You can think of it as a lossy version of that, where you kind of boil everything down to a single integer. There are a couple of reasons for doing this. One is it's much easier to reason about integers in SMT than it is about full vector clocks, especially around the inductive proofs. So because you have integers, you end up getting this kind of, so when you think of your DAG of flow where you have your operations executing on multiple nodes and they're branching and merging, if you treat everything as a single integer using these Lamport timestamps, what you get is you have nodes, you're processing operations, and then at some timestamps, you might have several nodes performing concurrent operations. And it's very easy to identify that and have users declare this operation ordering over those because they say, oh, if these integers are different, then I have an ordering. If they're not, then fall back to the user-defined conflict resolution policy. Becomes a bit messier with vector clocks because now you have these more complex arbitrary DAGs and it's harder to reason about exactly how you end up sorting and smushing this down into determining which operations would be concurrent or not, especially because we're doing this pairwise ordering. It makes things a bit messier. I've had a couple chats where there might be some cool tricks we can apply of having two layers of induction where we start with this inductive proof at the bottom, and then we have induction over, if I added one more element to my vector clock, would my proof still be true? Which I'm kind of intrigued about, but I haven't sat down and done the math, but it's mostly in making the proof go through is where you run into a bunch of challenges, and it ends up just being a lot more straightforward with Lamport timestamps for now.
They also, vector clocks also produce a massive programmability issue here. What you intuitively want is there to be like a series of operations that mostly are sequential, and then occasionally you've got these ties, you've got these sort of like sets of operations that are all concurrent, and you have to linearize those. But that happens, that's over, and then we're back into more of a sequential world. What you really don't want is to say that all the operations secretly have this unknown potential interleaving operation at all times. That's really inconvenient. You would really prefer that not to be true. With vector clocks, if you have one or two stragglers or a partition in the system, you wind up getting this all of history has got some parallel, potentially concurrent with literally all of it thing going on. And there's literally no answer to which of the conflict sets, if you will, should I put these like partitioned elements into. They go into all of them. It makes your conflict set suddenly become everything in the entire system. So in the Gallifrey era, we kept trying to figure out ways to like expose this to the programmers, let this be reasoned about more directly, and it doesn't really work out well for them. Like if you were using vector clocks to resolve causality precisely, that's great, but you probably need to do that while exporting causal consistency and just telling the user things might change out from under you for reasons you don't understand. because we linearized some causally independent branch right after you. I think beyond the SMT issues, Lamport clocks just are easier to explain.
Cool, thanks. And if you can hear the cat in the background, she's happy to hear from you also. Thanks.
That's good. I'm glad.
So I think, I mean, we have a few minutes left. Quinn's question kind of gets at this. The more complicated CRDTs we talk about, like RGA and stuff, is that what we're kind of getting at? Or Russell brings up like how things work in ad hoc meshes with this stuff and data being completely offline for a long time, having to send all these sets. Like, I guess this reasoning about this user reasoning, which I think you're right, is explained really well in Lamport clocks. But in systems that we're seeing are really these really difficult collaborative editing kind of stuff situations. Is that where you kind of see the difficulties kind of lie and you know, between the user and the actual like you know, convergence and correctness that we want, determinism from these properties is what I want to say.
Yeah, absolutely. That's another big thing I guess we didn't touch on earlier when we were talking about RGA, is another big piece of the puzzle that's yet not completely solved is how effective our pairwise approach works for defining the semantics of RGA. If I start with like a regular vector data type, and what would a pairwise conflict resolution policy look like for specifying one of the classic CRDTs? Unclear. That's research that needs to be done. So it's possible we'll need a different model for specifying those. I think the like this constraint is really kind of fun and interesting to play around with, is the fact that whatever constraint we have the user annotate has to be in terms of the existing data type. So that means that you do end up a little bit constrained. Also, similar thing, you have similar constraint to SMT, which is you can't arbitrarily reason about the entire history of this CRDT in this conflict resolution. So, but I think the best answer I can say is to be seen. But it is a challenge for sure.
I will also say vector clocks are great. I don't mean to bash vector clocks. They are incredibly good if you want causality, and there are lots of applications that specifically want causality. I mean, like your classic like message response idea in Facebook absolutely wants causality. They work really poorly if you're trying to ask the question of, I have this conflicting operation, which part of the history of conflict should I really think of this as being a part of? And that's a question that is almost never asked by users, but is frequently asked by developers and implementers.
Yeah, for sure. I think that's a lot of this is the point too. Again, this kind of bridge between conceptual understanding of somebody writing a program sequentially to get the output of what they expect or what they want their system to do based on that operation list versus, yeah, I think that's like really the kind of always the wrestling, right? Like, and this is why like a lot of the CRDT stuff typically has been, you know, we'll provide a database or we'll provide a system where you don't have to know about it that way. So somebody's kind of in control of that versus, again, I think what you're exploring in this paper is, again, how can people reason about this without having to reason about it all the way through, right? I mean, that's kind of a, again, I think there's actually so much that opens up here in the HCI side of as well. So I got a few minutes left. I don't know if anyone wants like one more question, or if May and Shadad, you guys want to kind of culminate. I mean, this is really interesting, I think, in terms of where the future work is going and the VLDB stuff. And we linked a lot of the stuff coming out from the whole group and the PAC work. But maybe any way that you want to kind of wrap up kind of where all this is headed in your mind. Oh, we have one more question. I'll give it to Russell then, actually.
Oh, we'll I mean, just a real quick one, since you mentioned you know, complex types like RGA. I'm wondering about things like maps. They're not mentioned in the paper either, and they're pretty common. Like, you know, like dictionaries, you know, like associative kind of thing. Anything like that in the future?
I was pretty sure we could do maps, but maybe Shadaj is gonna correct me.
Yeah, so we use maps in the synthesis, but we don't synthesize map CRDTs. I don't think there's any reason why we couldn't. I think the reason we don't have it in the paper is at the time MetaLift would not support identifying maps in your input code. MetaLift is a relatively new framework. We added support for sets to MetaLift just for this paper. And I think one of the interesting challenging pieces is the fact that there are no good theories of maps in SMT solvers, so like CVC5. So CVC5 does, which we use for verification, does have a theory of sets, which is great. Maps, actually, even though we do support them, we end up just boiling them down to bounded verification in those cases because there's no formal theory. So we just say, look at large enough maps and hope it's correct and spit out a very large, loud warning to the user that we're not actually guaranteeing 100% correctness just because there's no theory yet that we can use.
If you're thinking things like, can't you axiomatize it as a set of pairs? You can, but if you ask CVC5 to do that, it never comes back.
Yeah.
And you guys, you all have,
great,
you have
thank
this
you.
multimodal. That's right. Yeah, you have this multimodal thing too of like, you use Rosette, right, for pieces of this. You use, yes. So it's interesting. I think there's like probably a whole talk we can have just how to implement the research like this, right? That's seems like a very interesting thing because you're mixing everything, right? So.
Exactly. Yeah. No, I'm actually working on a blog post right now, which is kind of trying to take a code first approach to walking through Katara. So it goes into the code base and kind of says like what actually goes on under the hood in all the nitty-gritty details. So that will cover a bit of that.
That would be awesome. I think that's for like everyone here, I think researchers putting that out is always a really great thing, right? Because that idea of tying into the practice, right? So I was excited when I saw this too and thought, oh, you all use Rosette, but then you also use this, and like, again, this maps piece actually comes out of that, right? Where you have the certain caveats with the underlying implementations. Cool. So I guess, to my previous point before Russ's question, was there anything else you all want to kind of culminate in the kind of future vision of this stuff? And, you mentioned already what to look for, but I don't know if you wanted to add anything else to that.
I guess within the CRDT space, we're definitely excited about kind of the specific problem of like identifying opportunities to use CRDTs by analyzing existing applications. I think is like the key thing that we're really excited about for bringing applications into this Hydra world. Beyond that, there's a lot of really cool PL stuff happening in the group, working on type systems for reasoning about data flow that May's been leading. We've been working on developing compilers for taking Datalog and Daedalus and running them with really fast Rust execution systems, something I've been working on. So lots of, we're a distributed systems group and we have a lot of distributed systems PhDs, but especially because of May, we are doing a lot of PL stuff too. So definitely keep your eyes out. There's a lot of really exciting stuff coming down.
Yeah, and I'd say that like the only takeaway from Hydro that we haven't talked about that I would tell you to do is put a systems person, a databases person, a programming languages person in a room, and don't let them leave until they solve these problems. It's working for us.
That's an awesome pitch for the lab as well, right? Yeah, I having kind of been in and around that, I think it's super important that you want all these people together to make really great research happen in practice. And following a lot of the Berkeley way too, where you have 5 authors on it, people are working, students working on all these things, and it's a really great way because a lot of PL, right, is like one person trying to do the thing, right? For systems, you have like 6 or 7, so it's really nice kind of putting that all together. So we'll end it here. I know Quinn had another question, but we can. I want to give people back some time. We've been doing this for an hour, but we can take some of those offline. As I know, May and Shadaj have been awesome just in answering stuff and putting this together. So thank you to both of you for coming on here and doing this and doing this kind of awesome thing. That's super claps. Thank you for everybody here who looked at the paper, read the paper, thought about the paper, had discussion points and questions. And we'll do another one of these again soon. We're working with some other guests and some papers to come by. And thank you everyone again. And I'll make sure when we post the video for this, contact information on Twitter and stuff for May and Shadaj, so people can hit you all up for more questions and thoughts as they go through stuff or go through the code even. So cool. Thank you all.
Thanks for having us. Give Katara a try, find bugs, file them on GitHub. We want people to use this, so definitely poke holes in it.
Yeah.
Nope.
If you don't mind turning off the recording, we'll hang out and answer more questions.